irrationality as well as specifically proving that this number is irrational. Now, first of all, what is irrationality? Now, obviously, you know what irrationality is. A number, alpha, is defined as irrational if there does not exist p and q in the positive integers relatively prime, or coprime, is a shorter word, such that p divided by q is equal to a. Or in other words, a is not in the set of rational numbers. It's in the complement of the set of rational numbers. So that's our definition of irrationality. And sometimes this bare bones definition works. Like, for example, if we want to prove that the square root of 2 is irrational, we use a proof by contradiction. Assume that it is rational, right? And then all we have to do is square both sides. Then multiply both sides by q squared. Now, of course, this implies that p squared is even, which implies that p is even. But if p is even, p squared should be divisible by 4, which means that q squared should be divisible by 2, which means that q is even. But that means that p and q are even, when in our definition they have to be coprime. Which means that clearly our definition does not hold, so rad2 cannot be in the set of rational numbers.
Who proved that the rad2 is an irrational number? Was it a Hipparchus?
Not sure. Okay.
And what year was it?
Not sure.
Okay.
So now we've proven this thing very, very simply. But sometimes this proof just doesn't cut it. Like, for example, with something like e or pi. How are you supposed to do this? Well, what we can do instead is use something called Louisville's criterion. Oh my god, these are heavy. Now, what is Louisville's criterion? Well, the first thing we have to do is, let's go back to the square root of 2. Let's say we're trying to see how close we can get to the square root of 2 with a rational number. Like, for example, what's the rational number with denominator 1 that's closest to the square root of 2? Well, 1 over 1 is closer than 2 over 1, clearly, because the square root of 2 is approximately 1.41423 something. Okay, so then, how close can we get when dividing by 2? I think 3 over 2 is our best bet. So this is 1.000. This is 1.500. Now, if we're dividing by 3, well, we can try 4 over 3, which is 1.333. Then, let's say we're dividing by 4. Well, we could have 1.25 or 1.5. I'm pretty sure 1.5 is a little bit closer. Oh, so we'll go 6 over 4. Okay, then if we're dividing by 5, I think our best bet is 7 over 5, because that's exactly 1.4. Okay, then we can try dividing by 6. I mean, what will that give us? We could try dividing 3 over 2, 6 over 4, 9 over 6 again, or we could try 8 over 6, which I think is a little bit closer with 1.333. Yeah, it's closer. So then you can try dividing by 7, and I actually have a sequence of these all listed out on my paper. 8 over 6. Okay, yeah. And the next closest one is, when dividing by 7, 10, because that's about 1.428, and so on and so forth. So these are clearly getting closer and closer and better as you move forward. So what happens when we try to graph this by, let's call this a sequence AN. What if we try to graph every point n comma AN? Well, it comes out looking a little something like this. So as you can see, the difference starts from 0.41 blah blah blah, which is the square root of 2 minus 1, and then it immediately drops down in a very eerie fashion. So, I mean, you probably recognize this function from somewhere. And that's because this almost exactly correlates with 0.421, not sure where that number comes from, don't ask me, divided by n squared. Now, why the n squared factor? Why does this look so similar to a function x to the minus 2? Well, it all comes from the algebraic degree of the number. Specifically, the square root of 2 is the solution to a polynomial with integer coefficients of degree 2. So this is the lowest degree polynomial it's a solution to, and as you can see, there's a big fat 2 right there. And of course, can you predict what that's going to mean for rational numbers? Well, rational numbers are always the solution to a polynomial of degree 1. That's a rational number. A polynomial with integer coefficients of degree 1. So, can you predict what the correlation is going to look like if I tried to draw up a sequence for a rational number instead? Well, what I did was I picked some random prime number so that we wouldn't get like a super early divisor of it somehow. So I pick a random prime number. In this case, it was 991. And then on the top, I just generated some random number that was higher than it, 1027. And so, what do you think the correlation is going to look like here? Well, the algebraic degree of this is 1, which means that hypothetically it should look like cx to the minus 1, right? And of course, when you actually do the numbers, oh my god, this is a thick booklet. Yeah, it's hard to separate the pages here. Okay. When you do the numbers here, clearly, as you can see, it has this weird zigzag pattern, but I'm not going to focus on that today. What's more interesting is that it follows this 1 over x correlation. As you can see, it shrinks much slower than, we should have printed this double-sided. It shrinks much slower than this guy right here. This one practically goes to 0 instantly. This one takes a much longer time to do so. So, paradoxically, rational numbers are approximated worse than irrational numbers. Which is pretty strange.
What does that even mean? Can something be worse in math?
Yes.
In what context?
Worse in that it converges slower. And naturally, when you're approximating something, you want it to converge fast. Which is why, if something doesn't do that job, it's called worse. Yes, there can most definitely be a worse in math. Okay. So now, there's also a very special kind of number. A transcendental number. Now, a transcendental number is a number that doesn't follow this correlation for any integer. Okay. So, for example, some recent research on pi has shown that approximations to it fall at around 7.2, which aligns with the fact that we know it to be transcendental. 7.2 is, of course, not close to any integer. It's not an integer. Now, of course, the other kind is numbers whose approximations converge so fast that they outpace any function of this form. For instance, the Louisville number, which was the first proof that a transcendental number existed. Now, of course, when you look at this, it'd be pretty easy to write out the first few terms. Right. So here you go. And clearly, you can see that these approximations get almost exponentially better. So the approximations to this function increase at a rate even faster than an exponential, in fact. An for L decreases at a rate analogous to C over x factorial, or I guess n factorial. No, x factorial. So, this is pretty huge. And of course, as you should know, x factorial will eventually be greater than x to the n for any positive integer n. And that means that when you flip these things over, you take the inverse, then this is always going to be less than this. Same thing over here. Okay. Well, eventually. Okay, so that's really nice.
So you don't have to look at the lecture note?
I do. So now, okay, that's, I guess, the end of this blackboard. Should also have a blackboard behind this, but let's try to use this space for now. So now, let's describe the zeta function.
Oh no, zeta function is a big thing, so we'll take.
Okay. Well, the zeta function's description itself is relatively simple. So zeta of s is equal to...
Okay, can you give us some history behind it?
No. Well, it was invented by Euler in the early 1700s, but of course everything discovered by Euler is named after the second person to have discovered it. Otherwise, everything in math would have been named after Euler, which is why it's now called the Riemann zeta function, because Riemann was the second person to rediscover this function and then study some of its properties. So, that's a very brief history. So now we have zeta of s is equal to, let's say we have n equals 1 to infinity of 1 over n to the s. Now, of course, if you remember your calculus, you know this doesn't converge if s is less than 1, less than or equal to 1, theoretically. Now, you might be wondering, well, how do we come to things like the Riemann hypothesis, where somehow we're plugging in complex numbers into this function? How do we do that? Well, that comes from analytic expansions of this function. Most of them coming from this guy right over here. And Euler's theorem, Euler again, allows you to raise this to an imaginary or complex power, which in turn allows you to use logarithms in funky ways in order to raise a normal number or an integer to this funky power. But that's not what we're concerned about. We're concerned about exclusively the classical definition, which means we're concerned about the numbers where it's always supposed to converge. S is equal to 2, s is equal to 3, 4, 5, maybe even fractional values, stuff like that. So, theoretically, when you're graphing it, the real function, no analytic extensions, it should look something like this, with a pole at 1, and then slowly converge to 1. Well, not slowly, it's very fast, actually. Okay, I mean, zeta of 2 is already about 1.6, zeta of 3 is about 1.2, zeta of 4 gets smaller.
When you say very fast, what do you mean? Speed of light? There is no room for time over here.
Okay, what we mean by a rate of convergence is specifically essentially the derivative of this function. I mean, I don't get why you say there's no room for time when parametric functions exist. But okay, so anyway, this is essentially the zeta function, or at least the branch that we like to study. So, zeta of 2, for instance, is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, etc. So today, we're going to prove the irrationality of this guy right here. Alright, so how do we do that? Well, let's start from the beginning by defining a nice integral for it. So zeta of 2, since we're actually starting the proof now, I think it's probably a good idea to erase.
By the way, this is about 20 minutes of the lecture, so you think one quarter or half?
About 1/3.
1/3. This is the pace you're gonna maintain tomorrow, or even faster?
Hopefully faster, because we're not going at the fastest pace right now. Okay. So now, here's what we want to do. So we start with zeta of 2, right? The basics. This is equal to the sum of 1 over n squared. So now, here's what I'm going to do. I'm going to break this up into 1 over n times 1 over n. Right? So that's already pretty interesting. But now, let me pick up my booklet, because this is where things start to get heavy.
What page number are you on?
Let me see. According to the booklet, we're on page 6.
And that is 1
out of 15, I think. Okay. So now I'm going to do something that looks random. 1 over n, I hope we can all agree on this.
Did you give the credit to Professor to help you?
Not right now.
Oh, tomorrow, okay.
1 over n is equal to 1 over n minus 0 over n. I know, sounds stupid. But now, consider that that's equal to 1 to the n over n minus 0 over n to the n. So, this is equal to x to the n over n, with bound 0 to 1. And what was the motivation for all of this? Well, this looks suspiciously like a product of the inverse power rule from integration. In other words, this is equal to the integral of x to the n plus 1, or n minus 1, from 0 to 1. Right? Oh, okay. So now what I'm going to do is I'm going to set this equal to all of this. So we have the sum from n equals 1 to infinity of what do we have now? Well, clearly we have the integral from 0 to 1 of, let's call the first one of these x1 integral. So for now, I'm just going to call the unit square in area A, because it's a lot more concise to write. So now we're integrating x1, x2, n plus 1, dx1, dx2. Okay, great. So this is nice, right? Now I'm going to do something, and hopefully you will see why it's true. Because it should be apparent to you that the integral of a sum is equal to the sum of integrals. Thus, what I'm going to do is I'm going to use Fubini's theorem and flip these guys. So I'm going to write this instead, since this is just a huge sum. This is going to be over A. This guy is going to sneak into the integral. Alright, let me make sure this is what I'm supposed to be getting. Oh my god. It was literally right there, and I screwed it up. Holy crap. Minus, 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 minus. Good thing I checked my notes. Okay. So now, what's this going to be equal to? Well, I'm going to define a new variable m to be equal to n minus 1. Why? Just so I can put this in a more familiar form, so that you can see what's up ahead. Alright, and now what do we have here? This is what we call a geometric series, isn't it? And what's the sum of a geometric series? You probably remember from calculus that that's going to be equal to one divided by a 1 minus x1, x2. And now do note that this vanishes when you're at the boundary of A, but we'll just take this to be... Did it just split clean down the middle? We'll just define this as an improper integral. Okay, So this is our final integral for zeta of 2. Good. So now here's what we're going to do. Let me just flip over there, flip over there. Oh crap. Do we want to do this or do we want to skip to the final
No,
limit?
skipping. Ready?
This is a little bit intensive, but we can go through it. Okay.
You just want to see that before you do it in front of thousands of people.
Oh my god. Okay. So I'm going to erase everything on this board except the final answer that we have here.
With my hand getting tired, if you don't meditate, how long will that take?
Probably an hour.
Okay.
Okay. Great. So let's talk about what we're going to do next. Logically, what happens if I take a rational approximation to zeta of 2? Well, the best way to rationally approximate an infinite sum is to take a partial sum. So let's take an approximation. An is equal to, well, let's call it m or k. It's probably better. N is equal to 1 to k, 1 over n squared. So continuing, naturally, a partial sum is going to be the best rational approximation we have. But what happens with a partial sum? So of course we're going to need to make a common denominator. So this is going to be some integer on top divided by the least common denominator of 1 squared, 2 squared, k squared. So what we're going to do is we're going to show something very elegant. This is actually equal to this. So how is that possible, you might ask? Well, it's because of the way the least common denominator works. Let's say we're trying to find the least common denominator of these 7 numbers. Right? So what we're going to do is we're going to search for what are all of the prime numbers that are below the last number. Well, there's 2, 3, 5, and 7. Pretty simple. Okay, so now you want to ask which of these numbers contains the highest factor of each of these. Like, for example, which of these numbers is divisible by the highest power of 2? Looks like it's going to be 4 with 2 squared. Which of these is divisible by the highest power of 3? Looks like it's going to be 3 with just 3 to the 1. Same with 5 to the 1 and 7 to the 1. So that means the lowest common denominator is going to be the product of all of these guys. And this is going to be useful later. Now, what happens when we're taking the lowest common denominator, 14, 15 numbers? But it's not that crazy. Why? Because clearly, this is divisible by 1 and 1 squared, 2 and 2 squared, 3 and 3 squared, 4 and all of its factors, and 4 and all of its factors squared, 5 and 5 squared, 6 and all of its factors, and 6 and all of its factors squared, 7 and 7 squared. Which means that any of the prime numbers higher than 7 squared obviously aren't divisible by anything on the list. So we're only searching for these guys. What makes that even better? Well, we're looking for the number divisible by the highest power of 2. It's 4 squared. That's divisible by 2 squared squared. Then we're looking for the one with the highest power of 3, which is obviously this guy right here. 3 to the 1 squared. 5 to the 1 squared. 7 to the 1 squared, which means it's just going to be the product 2 squared squared, 3 to the 1 squared, 5 to the 1 squared, 7 to the 1 squared. Hopefully you can see that that's just the squared version of the least common denominator of the first 7 numbers. So for that reason, hopefully you can intuitively see why these two quantities are equal. Okay, so now we know that this is true. And to denote this, we're just going to write dk squared. So the least common denominator of the first k integers is now dk. So every partial sum is going to be something of the form zk dk squared when reduced to just raw integers, which means that these are going to be the best rational approximations that we have. Alright? So if every single rational approximation looks like this, can we define an integral form for these guys? Indeed we can. I really want to skip this, but I guess we are not going to do that. So, if we're doing a partial sum, now let's try to find an integral form for this. Zeta of 2 minus the partial sum, the error function. Okay. So, that's just going to be every single term besides the finite ones at the beginning that we've just cut out. So that's going to be 1 over k plus 1 squared, 1 over k plus 2 squared, blah, 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 blah. Okay, so that's just equal to, you see d sub n, as I mentioned earlier, it's going to be, just going to multiply all of the numbers with the greatest prime factors. So in other words, actually, here's what we're doing. We're essentially searching for what's the greatest power of each prime number that's less than, well, our total. And of course, in this case, and I'm going to generalize it by saying p instead of 2. So now, what does that mean? Well, we want p to be less than log sub k of
So
n.
my question is, then zeta 2 and zeta 3 would be the same strategy?
No, not at all. Okay. Well, kind of, but not fully.
What percent then, if you have to?
Like 40%.
40% same, 60% different. Okay.
Okay.
And you expect it to the same for zeta 5? 40% same, 60%?
0% the same, because we've already tried the method that we used here on zeta 5, and it seems to not work. If it did work, we would have had a solution by now.
And Professor who helped you, he doesn't even have it? Professor Warren? No?
No? Okay.
How big even would that be if someone comes with a proof of zeta 5?
Can I please continue?
How big would that be?
Okay, can I continue?
No, would that be bigger than zeta 3?
How should I know? I don't know how academia would respond because I'm not an expert on the applications. But it would probably be bigger than zeta 3. Okay, so what is this equal to? Well, we abracadabra. No, not abracadabra really. What we're instead doing is the log conversion formula